organization of this conference. My presentation is in line with the previous one. I will present the laboratory and also the development and the implementation that we made about this microgrid islanding operation and the black start procedure. I will make this first part about presenting the concept that it is already introduced about our vision of the microgrid, the validation of the concepts, and after we go to this laboratorial part. Here we have this architecture of the microgrid, and it is explicit that is a flexible, active and controllable LV system that should include microgeneration, storage, electric vehicles, and any kind of loads that already exist. This is a more explicit diagram of a possible architecture of a microgrid. It is very similar with the architecture that we actually have in the laboratory, and I will show you an animation of how for example, in this case, voltage control in these microgrids can work for the integration of electric vehicles and other controllable loads. First, we have the power consumed by the electric vehicles. You know that there is an important load for the system, since the EV chargers has a huge power rating, and it is increasing. And in this case, you can see that the voltage is expected to drop to critical. In some cases, in weak networks, it can drop to very low levels that are not compliant with the standards for power quality. If you reduce the load, you can solve obviously the problem, but we will create another problem in this case for the EV chargers, because the users need to wait more and more time to the charging to be complete. But in this case, if you have distributed energy resources that you can put injecting power in the grid, probably the voltage will increase again, and using the microgrid management system, you can increase the load again and use this flexibility offered by the AVs and in general by any kind of controllable load to balance the low voltage grid by itself, making it possible to operate autonomously in some cases. We have been involved in many projects about microgrids, European, international and national projects. In these projects we developed, as you saw previously, we developed many models, many control strategies for the microgrids, having in mind all of the aspects as communications, as safety measurements, as everything. And I would like to introduce this INNOVGrid project. It is a project that started about 10 years ago, and it is the reference project in Portugal, and one of the reference projects internationally for the first implementation of some of these smart and microgrid concepts. It deploys for the first time the smart metering infrastructure in Portugal. It is INESCTEC collaborates in the definition of the reference architecture for the operation and the control and the implementation of all this grid that is actually working in Évora, in Évora city in Portugal. Going to more specifically to the laboratory, this laboratory is working since about 10 years ago. This image represents our vision to the smart grid development and research, with the three key aspects: the power systems that deals with the modeling, the control, everything about these microgrids, the power electronics as the physical implementation of the interfaces, and the ICT and cybersecurity, which, as you know, links everything together and allows for these advanced functionalities. I will present a little bit about some of the resources that we have. We are continuously upgrading and updating the laboratory, but we have storage units, large storage units that can work in interconnected and islanded mode, which is very important to have this kind of microgrid experiments. We have microgeneration units. We have two kinds of them. We have commercial units, and we have prototypes developed in-house. The commercial units are very important to validate the solutions, the control solutions that we develop, because they are willing to be installed in the field where the kind of equipments that we can find are very similar. We also have communication and metering equipment, which is a key element in these implementations. And we have electric vehicles. We have several electric vehicles, and we have only developed EV chargers to implement the smart charging and vehicle to grid functions. Here is the infrastructure in more detail. Some numbers about the equipment that we have. It is all of them. It is size to implement a microgrid with a realistic power scale. These are the commercial equipment that we use to validate the control mechanisms. These are the pictures of the previous versions of the microgeneration prototypes. These prototypes have been continuously developed to integrate more and more functions, as I will show you in the next slide. And in this case, they are developed to demonstrate the control methods for the microgrid. They are single phase inverters. Now we also have three phase inverters, and they have this bidirectional communication with MGCC, which is the microgrid central controller that we also have installed in the laboratory, and they have local and remote control, as we will see in the results. They have different purposes. The bidirectional AV charger has an added function, which is the capability of be bidirectional, as the name says, which is very important for a microgrid, as it is the balancer of the power flow, especially in islanded mode. And we have the infrastructure that connects everything together. It is a very large switchboard, when we can put loads, microgenerations, storage. We can put cable simulators. We can put non-controllable loads. We can connect everything together and easily reconfigure the architecture of the microgrid. This is the microgrid control architecture developed, and it corresponds to the implementation that was done in the laboratory. Here, I will make this point about this laboratory. This concept has already been exported, as I can say, to Morocco in this case, in this secrets project. Probably some of you know it. There is currently a laboratory in Kenitra University that is an adaptation of our laboratory to their needs, and we also receive fellowship researchers that are doing his PhD to work with us, and also to receive some of this know-how that we already have in these topics. Going specifically to the control functionalities that we have in the microgeneration units, we implemented this droop control, when you can see the dead band that corresponds to a normal scenario, when the power injected, in this case, it is according, for example, for a PV, it's according to the MPPT, the reference that is given. And when you have abnormal conditions in the voltage, the power can be increased or decreased to help in the control of the network voltage. For the EV charger, this droop is more sophisticated, because you can even reverse the power flow within this vehicle through grid concept. That is a concept already being demonstrated in the field in some countries, which, when operated as a fleet with large number of vehicles together, can represent an important resource for the grid control. This is the network implemented in the laboratory. It's exactly as it is here. This is real equipment that that we have there. As Professor Lopes says, the voltage source inverters are the main support for this operation. These voltage source inverters have internally a bypass switch, or they can work in interconnected and go to island mode, and after they have a synchronization mechanism and go to interconnected mode again without affecting the loads and the possible consumers. We will see results about the operation in interconnected mode. In this mode, it is important to control the voltage, since the voltage is very dependent on the node of the network which the resources are connected. And as is expected, in the farthest nodes, in this case node 4, it is this over and under voltage, in this case over voltage problems are more visible, since the impedance is bigger. And we demonstrate here that with these power groups, power voltage groups, PV groups, no, not here, right. We can solve or minimize these over voltage problems. This is important to comply with the standards, to avoid tripping of protections, but also to ensure the maximum yield from the renewable energy sources. In this case, we have the opposite. It is an under voltage problem, where it is demonstrated that the AVs cannot also decrease its charging rate, but if they are capable of that, to inject power and put the voltage in more acceptable levels. In the island mode of operation, it is important to show the contribution to the frequency regulation, because in interconnected mode, this kind of small resources don't have impact on the frequency, but in islanded mode they have. They can react into manners in primary frequency control, that is instantaneous response to with the active power to frequency deviations, and it is proven that if the amount of power that is controllable it is considerable, they can have huge impact in the frequency regulation. And there is also a capability to control to contribute to secondary frequency control. This control strategy is based on the reserve, because these resources are controllable in this range. It is related with the reserve capacity that they can give, and it is shown up here that it is possible also to contribute to secondary frequency control in islanded operation. The black start is the other topic that you see in the previous presentation as a key aspect for these microgrids. This is the procedure that we follow to make this black start experiment in the laboratory. And here you can see the frequency during this procedure with and without the power frequency drop. And you can see that if we have power frequency drop, the frequency deviations are smaller, in fact. DV response can be very useful here, since it have the bidirectional capability, as I show you before. In the conclusions, we found that these power voltage drops are very important to make voltage control of mainly low voltage grids. We have demonstrated this in another European project. This is the Sustainable project, which has a field demonstrator operating since 2016, I think, 15 probably. With more than one microgeneration unit, it is easy to make the parallel of the power injection without communication channels if they are not available. The coordination of the microgeneration and AV charge, as you see, can increase the efficiency of the system and the renewable energy penetration. And also, it's not here, it is also possible to improve the usage of the installed capacity, for example, in the transformers, because most of the power can flow within the LV network. For the frequency regulation capability, it is proven that the AVs or any kind of storage unit are capable of balance the microgrid and keep the frequency within an acceptable range. So these kind of concepts are very well known. I think that these demonstrations are important because we have this experience in Portugal. It's very important to have demonstrations as much realistic as possible to make the DSOs to trust in this kind of solutions. This is seen for us as a very successful story. This starts with more than 10 years ago with some projects. I put here the Microgrid project as it is a reference project, as I told you, in Portugal. It is installed, it has been upgraded and updated with many functionalities. We are involved in most of them. In 2015, we installed this low voltage control in a small village, also in the Évora city, but just this village. It is a very particular network. It is very small, with I think it's 200 kVA transformer, but they have lots of prosumers with PV plants installed, and it is identified by the Portuguese DSO as a case study for this kind of control methods. And this year, in a project that will end this month, with new inverters. In this case, they are three-phase inverters that we developed also in the laboratory, and we had some new functionalities like fault ride-through to resist to short circuits in the grid. All of this was validated in our laboratory, in an independent laboratory, and it is installed in field. And we have other equipment. It is a large consortium. We have GPTEC, for example, is a Spanish company that also has these battery inverters. And this network in Valverde was able to operate in islanded mode for 2 times without any kind of problems. They make the transitions, and this is done with all of these methods developed from 10 years ago, and we are still developing them, and we're still working on them. In terms of future work in this area, most of this future work is continuous work, is ongoing. We add, for example, to these inverters inertia emulation. It is because the electronic interfaces with the grid doesn't have inertia by nature. It needs to be synthetic, in this case inertia. But we have demonstrated this already in a project with a prototype, and is always an ongoing work. Let me conclude that you are invited to search more about our laboratory and to visit us. Thank you.